When I came to California, I was never expecting that the title of this talk is perfectly suited for the weather outside. It's anything but expected, but here we are. So I would like to talk about the tip of the iceberg of gravitational waves and explain you a little bit how eccentric extreme outliers can be used to decipher and unveil the origin of compact object mergers. And I'm going to mostly focus on neutron star black hole mergers for a particular reason. Right now, we have seen a handful of candidates, okay, 6 to 7, which have some evidence for being a neutron star black hole merger, mostly because they are consistent with the masses of an NSBH. However, some of them are probably not real, so maybe this one is a very massive neutron star, so that it's a binary neutron star merger. That might be a binary black hole, and for the upper event here, we're actually not even sure if it's a real event, okay? But roughly, we have an understanding that there are 3 to 4 very robust neutron star black hole mergers in the data so far. And very interestingly, 3 of them have very enigmatic properties. So for one, we have inferred a very large black hole spin-orbit misalignment. What you see here on the left is the posterior of the black hole spin-orbit misalignment. So these plots always work like this. You have the orbital angular momentum in the z-axis. On the left, you have the inferred black hole spin-orbit misalignment. On the right, for the neutron star. And we see that this one was very confident with very highly misaligned black holes. Similarly, another event, again, analyzed by the LIGO collaboration. Second event, also a very high black hole spin-orbit misalignment. And I already see Ilya nodding his head. This is very much dependent on what you actually assume for your parameter estimation. For the priors, I'm aware of that, okay? But there's a third event. Which was claimed by many independent studies this year to be eccentric, okay? There was one event which had claimed eccentricity at around 0.15, okay? And I'm not going to go into detail of whether these 3 evidences are real. Let's assume they are. And if not, maybe we see more in the future. What would it imply if that is real, okay? In particular, the eccentricity is extremely interesting because it is impossible to recover this eccentricity from isolated binary star evolution. What you see here is a simple toy model where you have just the Peters equation integrated, where you have the eccentricity at a typical stellar separation, so maybe something like 10 solar radii or so, and then you have the eccentricity close to merger at 10 Schwarzschild radii. Measured was something like 0.9, and measurable is, 0.1, and measurable is something like above 0.1 or so. In order to get close to merger and eccentricity close to 0.1, your eccentricity at a typical stellar separation needed to be 1 minus e of 10 to the power minus 4, 10 to the power minus 3, 0.99999. That's wholly inconsistent with the isolated binary formation channel. However, they are a very solid prediction from any dynamical channel. That's a plot by Mike Zevin for clusters, for binary black hole mergers formed in a cluster. And you see here the histogram of the eccentricity close to merger at 10 Hertz. And you see there's always a solid but rare prediction from dynamical channels. There's a rare abundance of eccentric mergers at 10 Hertz, so very close to merger. And that's shared among many different dynamical formation channels. So if that eccentric evidence solidifies, it means that not only can this single eccentric event cannot form from isolated binary evolution, but these kind of plots also imply that there must be a much larger fraction, which yet circularized, but came from the same channel. So these eccentric events really act as a tip of the iceberg. It's like going into the supermarket, you pay for 1 and you get 10, or maybe 100 or 1,000, we don't know yet. But actually, let's go into detail about this canonical main dynamic information channel in more detail. So let's think about dense star clusters, where you have these chaotic encounters between an incoming black hole and another binary coming in, and then there's chaos and you get an eccentric merger, okay? That works very well for binary black holes to produce eccentric binary black holes. However, with neutron star black holes, you have a bit of a problem because you have mass segregation. So what has been shown in many independent studies is that the black holes will sink into the center, do their thing, merge, get ejected, and so on, whereas the neutron stars live more on the outskirts of the cluster and only get into the core, to the dense core of the cluster once all the black holes are depleted, essentially. So while mathematically, if you want, there's no problem in forming an eccentric neutron star black hole merger in a cluster, the rates simply do not add up, okay? The rates of neutron star black hole mergers from clusters are way, way, way too low to fit, to recover LIGO. But I'm very thankful for Smarta's talk. She highlighted that actually most of our progenitor stars of black holes and neutron stars are not in binaries, but actually in triples or higher order configurations, where we have a close inner binary orbited by a very distant tertiary companion. And she also told us that there is the Kozai effect, the von Seipel-Kozai-Lidov effect. And what you see here is an illustration of it. So that's not a simulation whatsoever. It just tries to get the point right, okay? It's also not to scale, wrong time scales. But what happens here is that you have oscillations of the eccentricity in the inner binary. So on a very long secular time scale, you go from circular to very eccentric, circular to very eccentric. But this eccentricity oscillation always goes at the expense of an oscillation also of the inclination of the orbit. So there will be also always an oscillation of the orbital angular momentum vector of the inner binary, which you can essentially, I try to illustrate here, okay? There are oscillations. And in the case of neutron star black hole mergers, there's a particular reason, which I will explain in a second, why the black hole spins remain effectively constant in an inertial frame. Simply because in neutron star black hole triples, the oscillations of Kozai, of the orbital angular momentum, will be so quick that the black hole spins cannot efficiently follow the evolution of the blue orbital angular momentum due to relativistic precession. So what happens here is effectively the black hole spin orbit angle will also oscillate, okay? So let's see that in action. This is an actual simulation. As a function of time, you see in black the eccentricity oscillates and oscillates and oscillates until it reaches a very high value. And what happens then is you have a huge release in gravitational waves. It effectively it shrinks, it effectively decouples from the tertiary companion and undergoes an effectively isolated in spiral. So in the plot of gravitational wave frequencies against eccentricity, it will oscillate back and forth, back and forth, back and forth until it gets this very high eccentric punch, and then it undergoes an effectively driven in spiral. And this tiny bit here above, this is what we are after, okay? That's the residual eccentricity we are ending up. And actually, this is looking ridiculous, but that's the whole point, right? That's making the tip of the iceberg argument. This little eccentricity is so unlikely to get, and this is why you need to get a very, very high eccentricity to begin with. And similarly, you get a high, in red shown, a very high black hole spin orbit misalignment. When we do a full population, this is a histogram we are ending up with, where just to highlight again, blue would be the eccentricity at 20 Hertz from an isolated binary channel. Again, totally inconsistent to anything of 0.1. But for our triples, we get actually a very, very high fraction of eccentric mergers. So what you see, I just want you to focus on the red line, which is the cumulative distribution. To get anything, something like 0.1 or so, we get 30, 40% or something like that. And similarly for the black hole spin orbit misalignments, again, look just at the cumulative distribution. That's again isolated binaries. That's triples in red. It's not completely entirely impossible to get a high spin orbit misalignment from isolated binaries due to the kicks. However, it's much more likely to get a high, let's say more than 90 degrees on the left side from triples, okay? And also we find from our triple population synthesis code that the rate, whatever that means, rates are uncertain, matches actually LIGO quite well. One final comment, why are NSBHs so interesting for that? That's a complicated plot here, but I just want you to focus on one thing. We have the outer semi-major axis versus the inner semi-major axis. And when it comes to neutron star black hole mergers, if you want to form successfully a neutron star black hole in a triple, there are tight constraints due to the neutron star formation. What you end up with is with a very narrow strip in A2 over A1. Just because in order to survive the neutron star formation, your tertiary companion had to be very, very close, okay? And that drives all the fun, right? Because you can intuitively imagine that a closed tertiary companion gives you all of the eccentric mergers, the black hole spin orbit misaligned stuff, and so on and so on. And a tiny secondary reason is also the neutron star black hole mergers by definition have a very low mass ratio, which is why you have this eccentric effect, eccentric Kosa leadoff, which drives, essentially, it helps as well. In the interest of time, I will leave you with my conclusions. And I thank you for your attention.
Hey, Carl Rodriguez, UNC. Great talk. I have a couple of questions on the pop synth side of this stuff. So for this to work, right, you have to assume the black hole neutron stars get essentially no natal kicks, right?
No, that's a very good point.
Oh.
Yes. So again, is it this one? Right. Yeah. This is exactly what I expected. Mm-hmm. So a natal kick of the neutron star, you would intuitively imagine, okay, your wide tertiary, loosely bound tertiary companion gets immediately essentially kicked, right? Or unbound, your outer orbit. However, this, what really matters here is the kick the inner binary center of mass receives as a result of this natal kick. Mm-hmm. And it turns out that the impact of the kick, let's say 200 kilometers per second, gets effectively reduced by the neutron star mass divided by the black hole mass. And that's a tenth. And this is why the natal kick, the constraint from the natal kick, is actually super weak, okay? What's way more important here is the mass loss associated with the neutron star formation. So you have the supernova, right? Many ejecta. And the reason for that is the mass loss will be essentially carried away at the current relative orbital velocity of your inner binary. So the closer you bring it, the higher the mass loss speed ejecta, right? And in turn, the closer do you need to bring your tertiary companion to survive it. So you end up with a very narrow constraint of A2 over A1. That again skews your surviving population a lot. But also it's good because the mass loss, when you want to form a neutron star, is actually not that uncertain, right? You have an OB star, and you go down to a neutron star mass. There's not as much freedom to play with as opposed to what we think is the natal kick velocity distribution.
Maybe. Oh, nice. Thank you for your talk. I have a question. I think I asked you this long time ago. But here in this context, you get the tertiaries so close in. Are you worried or are you concerned or thinking about the evolution that you will get with the mass that was lost for the inner binary with the tertiary and have a more wet interaction than what is often assumed in the eccentric causally dog?
Yeah, that's a good point. We didn't actually model the interaction between the mass ejecta and the tertiary companion, which I believe is your question, right? What we model is during the stellar evolution, we take into account all kind of detrimental effects during the evolution. So whatever, if the inner binary widens and this would enter the triple into the dynamical instability region, we throw it away, etc., etc. Or if the black hole kick disrupts it, blah, blah, blah. Okay, but we didn't actually model the interaction of the mass ejecta with the tertiary companion.
Cool. Yeah, in the interest, can you pass it back to Cheyenne in the interest of prioritizing early career questions?
Quick question. Great talk. Yeah, Cheyenne. So if you don't have a triple or you unbind your tertiary and you just have a wide neutron star black hole binary, I know you've worked on this in the past, but there are perturbing effects that can increase your eccentricity. Have you looked into whether that's a possible formation channel of getting these eccentric neutron star black hole mergers? Yeah. And if so, how would you predict that compares to this triple channel?
Yeah,
given?
But good point. To be clear, what you are, I think, referring to is a channel where you have ultra-wide binaries, so something like 10 to the power 3, 10 to the power 4 AU. And I do not think they can be responsible for that for several reasons. Simply as an ultra-wide binary is so loosely bound that you can easily unbind it, okay, for one reason. And for the second reason is when you look actually at the observational evidence for ultra-wide binaries, when it comes to massive stars, they are most often the outer binaries of triples. Okay, so what you would actually have to consider is a scenario where you have a triple with an ultra-wide tertiary companion, and then you need to think about whether the galactic tides and the stellar flybys can induce a sort of cascade effect, a very highly eccentric outer binary that then triggers interesting stuff in the inner binary. So that's why I'm not super... Yeah, I know, but I think we can talk about this.
Yeah, could the next speaker come set up? Great. Yeah, maybe we can take a very quick question.
Yeah, thank you for the talk. So just, I guess it's going to be my job to be the one careful about eccentricity claims.
Yeah.
The plot you have shown come from a paper that again use a uniform prior on eccentricity and then in spiral only waveform. Yeah. There has been follow-up work in which I'm not involved, where they use TOB waveform and different priors that prefer low eccentricity, and they obtain that it's still possible that it's eccentric, but there is a big peak at zero eccentricity now. Yeah. And so again, I know that's not the main point you want to derive, it's just a motivation, but we should really be careful. Eccentricity is very hard to measure. Yeah,
that's a very important point, and I absolutely share that concern. This was more like a proof of concept where I would like to invite you to assume that this is an eccentric, a real eccentricity that we have seen so far. And if you don't believe this one, maybe in the future, okay? So fair point, fair point.
Great. Yes, let's thank Jakob again.